Okay, let's take a look at today's lesson. We're going to look at ratio and roots tests. These are the last two tests that we learned, the 9th and the 10th test. The ratio test is good for a couple of things. Let's talk about those so you can write those in your notes. One thing that the ratio test is good for is it's very handy when we have an alternating series that doesn't match the criteria of alternating series, or if we have a series that has some positive and some negative terms but they don't alternate. That's pretty helpful for using the ratio test. Other things that you might look for in deciding whether to use the ratio test or not are factorials. If I see a factorial in a series, I'm going to think about using the ratio test because in many cases we're able to get rid of the factorials with this test. So in exponents, sometimes that's helpful, but mainly factorials and series that have negative terms in them, but they don't match our alternating series test. So those are some of the main, things that will be useful for this test. The test itself takes a little bit of time, and so sometimes students don't really like to use this test because it's a little bit time consuming. It's not as quick as the P-series. If you have a P-series, you're going to want to do that test. But it's really not that bad. Notice that the only criteria for us to use this test, there's not a whole list of things that have to be true. It's basically that it needs to be a series of non-zero terms. That's the criteria that we need to use this test. And it doesn't always work. Let's look at basically what we're doing is we're comparing to the number 1. Once we complete the test, we're going to get a number and we're going to compare it to the number 1. If the number is smaller than 1, then the series will converge. If the number that we get is larger than 1, then the series will diverge. And the test fails if it is 1. If the limit is 1, the test is inconclusive, so we pretty much have to scrap it and go to a different test. Okay, so that's the criteria. The way that it works is we take the limit. Now notice it's the absolute value bars are here. That's why this test is pretty useful when we have series that have some negative terms in them. It kind of wipes all the negative part out. And we do the absolute value of the a sub n plus 1. This means the next term. What I do is I take everywhere there's an n, I put a plus 1 by it, and that goes in the numerator. Then I put the original nth term expression in the denominator, simplify it, and take the limit. That's basically how the test works. Okay, so let's practice that. Alright, so we take the limit as n goes to infinity. Open our absolute values. So my expression is going to be 2 to the n plus 1 over n plus 1 factorial. That's what the numerator will have in it. I'm doing the a to the n plus 1 term. In the denominator, it's just the exact expression that we started with, 2 to the n over n factorial. And then what we'll do is we'll fix our complex fraction and start simplifying. Now I'm going to show quite a few steps here just so that we're really clear on what is happening and what's progressing. There are several of you in here that won't need to show every single step. But it is important to show the step at the beginning of your procedure that has the absolute value in it. Even though we know that this particular series isn't negative, we still need to show, because that's the way the test is designed, that we have the absolute value bars in it. And then as we start to simplify, since this particular series doesn't have any negative terms, we can drop the absolute value bars. So the next thing I'm going to do is I'm going to fix my complex fraction. And a lot of times I actually skip this very first step and go straight to the fixing the complex fraction step, which is fine if you would like to do that. So we're going to do the limit as n goes to infinity. We have 2 to the n plus 1 in the numerator along with n factorial. In the denominator, we're going to have n plus 1 factorial and 2 to the n. Hopefully we're all okay. I just took this right here and I flipped it upside down. So the 2 to the n goes in the bottom and the n factorial goes on top. Okay, so many times when I'm working the ratio test, I actually start with this step. I start with it already flipped, but it doesn't matter. Whatever you want to do. You can start here. This is the formal way right here. That's how this reads. And then fix it. So what our task is now is to simplify this. And hopefully by this time in the year, we're quite comfortable with taking this term and going backwards. This is going to be 2 to the n times 2 to the first. I mean, hopefully we're really comfortable with that. And that 2 to the n is going to cancel with this 2 to the n. And it's just going to leave a 2 in the numerator. Okay, has everybody visualized that with me? So the next thing that I'm going to work on are my factorials. And that's probably what we have the least amount of practice with, something that does trouble students. So let's talk about how to reduce these. Basically what I have, I'll go over here and do some scratch work over here. Basically what I have is n factorial over n plus 1 factorial. Now, numerically, we can kind of get a picture of what's going on. If I make n 10, then I know the numerator is 10 times 9 times 8 times 7, and the denominator is 11 times 10 times 9. And I can tell which is bigger, right? The one that's bigger is the one that I'm going to work on simplifying. I'm going to get it so that it reduces to the smaller one so I can cancel it out. Does that make sense? So I figure out which one is the larger one, and that's the one that I work on rewriting. So I would rewrite this as n factorial over n plus 1 times n factorial. And if I'm ever worried that I might have done something wrong, I just test and make sure that what I've done created the same string of numbers. So if n is 10, I still am matching on the top. Here we said would be 11 times 10 times 9. This would be 10 plus 1 is 11, and then 10 times 9 times 8. So you see it works. That simplification is appropriate. And then I would be able to cancel those n factorials out. So that's kind of how I would like for you to think about simplifying the factorials. And if you're worried that you've done something wrong, try something numeric. Try it numerically and see that if it's doing what you want it to do. Alright, so those factorials are going to go away. What I'm going to be left with is the limit as n goes to infinity. We agreed that all these terms are positive. I don't need the absolute value. In the numerator, I was left with a 2. And in the denominator, I was left with an n plus 1. And so we take the limit of that, and what does that tend to? Tends to 0. Okay, and this test is always comparing to 1. We just have to remember what the situation is when we compare it to 1. So 0 we know is less than 1. So that means that it falls into this first category. Our series is therefore, our series converges by the ratio test. Okay? Now some students really like this test, and some students really don't like this test. My goal is for you to learn how to use it and use it when it's helpful. Okay? Let's take a look at the second one. Any questions? All right. The second one, we're going to do the same thing. What I'm going to do is I'm actually going to, and I hope this isn't too troubling, I'm going to go ahead and start at this step, at the step where I fixed the complex fraction already. Okay, just that's where I'm going to start. If you don't want to start there, please don't. Just write this first step out like I did. But we do need to have the absolute value bars. All right. In the numerator, I'm going to have the plus 1. So I'm going to have n plus 1 quantity squared, and then 3 to the n plus 1 plus 1. And I'm going to leave it like that for a minute. You'll see why. Okay. And in the denominator, I have the 2 to the n plus 1. Now let's consider the original a sub n term. It would be down here underneath, and we're going to fix the complex fraction. So we're going to flip it upside down, and I'm going to have a 2 to the n here, and I'm going to have an n squared and a 3 to the n plus 1 here. And I got a little crazy with my line there. Okay. Alright, so now we have just a big mess that we need to sift through and simplify. The n plus 1 squared and the n squared, there's really no fixing that. It's just going to carry through. We can't simplify that n plus 1 squared and the n squared, so let's just pull it through. Do we have any negative terms in here that we're going to need the absolute values for? We don't, so we can drop them. So this is going to, let's rewrite, n goes to infinity. So I've got to carry the n plus 1 squared and the n squared with me. There's no fixing them. Alright, let's focus on the 2 to the n's. I think those are pretty straightforward. In the denominator I have 2 to the n plus 1. We know that that reduces to, or we can change the way that it looks by writing it as 2 to the n times 2 to the 1. Okay, we can see those 2 to the n's go away, right? And I'm just left with a 2 down here. We okay? Alright, now let's work on the 3's. I left it this way on purpose because we know that we get to go backwards like that, but why don't I just go backwards with each of these pieces? I don't need to make it a plus 2, right? I'm going to turn this into, I'll do a little scratch work up here. I'm going to turn that into 3 to the n plus 1 times 3 to the 1. I'm allowed to do that, right? I can just go backwards with part of it. And so this 3 to the n plus 1 is going to cancel with that one, and I'm going to be left with a 3. Alright. So we take the limit, go into infinity. Basically I have 3n squared over 2n squared, and this limit tends to 3/2. And we compare that to 1, and we see that that is larger than 1. So that falls into the second category here. So therefore, this series diverges by the ratio test. Okay? Alright, let's do our last one. Okay, so we have the limit as n goes to infinity. Okay, we're going to do the plus 1. So I have n plus 1 factorial over 3 to the n plus 1. And really visualize that this is down here in the denominator, and I'm going to flip it upside down. So it's going to give me a 3 to the n in the numerator and an n plus 1 factorial in the denominator. Alright, let's simplify. So limit n goes to infinity. Okay, we don't have any negative terms to deal with, so I'm going to drop the absolute value. This 3 to the n in the numerator is going to cancel with the piece of this, right? This is 3 to the n times 3, so I'm going to be left with a 3 in the denominator. Now let's work on the factorials. All right, let's do a little scratch work over here. So basically what I have is n plus 2 factorial over n plus 1 factorial. Now which one is going to have the bigger, which one is the bigger one? The numerator, the top one is, right? So when I rewrite it, I would rewrite it as n plus 2 times n plus 1 factorial over n plus 1 factorial. Those go away, and I'm left with the n plus 2 in the numerator. Okay, what does that limit tend to? Infinity. And it's okay, nowhere does it say that it has to be, that it can't be infinity. It just says it needs to be bigger or smaller than 1. And infinity is certainly larger than 1, so therefore this one diverges by the ratio test. Okay, how's that? We okay? Alright, let's take a look at our very last one, the root test. Everybody, okay. Alright, so first, let's see, we really don't have any criteria where it's going to limit us from using this. Pretty much it'll work. Our issue is going to be that it's not going to always work, because again we're comparing to 1, and if our limit equals 1, then the test is basically inconclusive and we have to scrap it and go to something else. So that's the only danger with this. Now let's talk about what this is good for. Let's talk about how it works first. First, notice that my nth term, my equation for my nth term, is encased in absolute value. So this works with negative termed series also. Works with those also. It's encased in absolute values, so it causes all the terms to be positive. It's taking the root of this expression and taking the limit, and we're comparing it to 1. Now, when would this be beneficial? Well, it would be really helpful if we had, like, our expression was raised to the nth power and we wanted to get rid of that n. You know, like this one right here. That's kind of troubling. What are we going to do with that? So using the root test is quite helpful for things like this, when we are raised to a particular power. This one is actually raised to the nth power, it's just not written that way. So that's when these would be useful. This particular test is useful if there's an exponent, a variable exponent that we want to get rid of. Alright, so let's work with that. Now, instead of writing it as a root, I actually prefer to write it as an exponential. So instead of writing it as the square root of n, how can I write that as an exponential? 1 over n. That's really a bit more helpful for me. That's the way that I like to use this. Instead of using the root, I use it in exponential form, because that's normally what we're dealing with anyway, are exponentials. Alright, so let's work on this test. So we are going to do the limit as n goes to infinity. We're going to write down our a sub n term, encase it in absolute value, and then raise it to the 1 over n power. So the first thing I would like to think about is, do we need the absolute value there? No, right? There will not be a negative term in there, so I don't need it. There are two ways that you can think about rewriting it. The way that occurs to me did not occur to some students earlier. I'm going to just show you how I would think of it, and then I'll show you a different way to think about it. I think about this as using exponent, basically a rule that allows me to rewrite this as e squared over e, that quantity to the n power. That's the way my brain thinks. Oh, thanks. N to the n. Okay, so that's the way that I would think, is to pull the n on the outside and then take that to the 1 over n. Certainly you don't have to do that. What you could do is just use, again, another exponent rule that allows us to take this and apply it to each of these exponents. You could do it that way instead. Either way is fine. You're going to end up in the same spot. So we're going to do the limit as n goes to infinity. Those go to 1. I'm going to have e squared over n. And what does that tend to? It tends to 0, which is less than 1, which luckily these are the same criteria. It converges if it's less than 1 and diverges when it's greater than 1. So if you kind of pair those two tests together in your memory, hopefully that will help you remember which way these are going. So if it's less than 1, therefore it converges by the root test. Okay? Last one. Limit n goes to infinity. We have 3n plus 4 over 2n raised to the n. That has to be, you have to show it encased in absolute value, even if it's not negative. They want to see the actual test. and then raised to the 1 over n. Alright, do we need the absolute value in this case? No, I'm going to get rid of that. These guys right here are going to go, they're going to multiply and get a 1. So I'm going to be left with the limit as n goes to infinity of 3n plus 4 over 2n. And what does this limit tend to? 3/2. Compared to 1, that is greater than 1. So therefore, what? It diverges by the root test.